Vapor pressure is one of the most commonly measured physical property in refineries and terminals. Ever stricter regulations combined with tighter process control make this measurement a key tool in increasing profitability of blending operations and refineries as a whole. Hi, I am Corentin Thierry, Sales Manager at Bartec US for Process Analyzer Technology Division, PAT. Let's take a look at one of the Bartec solutions for the monitoring our RVP, one of our best sellers from our Bartec Orb factory in Chicago, the P700 RVP Analyzer. Before digging further into the P700, one of the things we are as often asked to do is clarify what vapor pressure is. So vapor pressure is the measurement of the amount of vapors released by a product or a sample at a given temperature. How is this done in real life? So in a laboratory, we use a test apparatus like the one you can see here that contains a sample container, a bomb used to do a 4:1 ratio of vapor to liquid, and a gauge that will indicate what the pressure of the vapor released by the liquid is. So once the sample is exposed to the bomb where the vapors can get released, we will shake, agitate, and let the apparatus rest at a constant temperature of 100 degrees Fahrenheit or 37.8 degrees Celsius until the pressure gauge stabilizes. That stable pressure value is the vapor pressure of the sample at 100 degrees Fahrenheit. So there are multiple types of vapor pressure. You will hear terms such as read vapor pressure, RVP, true vapor pressure, TVP, vapor pressure of crude oil, VPCR, even dry vapor pressure equivalent, DVPE. All of these are different ways of measuring vapor pressure. For the most part though, RVP is the most important of those measurements. Now, why is RVP important? That is the question. Well, the first reason is because first, there is a regulatory aspect of RVP of gasoline. So gasoline, per the EPA in the US, for example, must meet a certain RVP requirement depending on the time of the year. So a winter blend and a summer blend of gasoline will have different RVP requirements. The second reason is a quality reason. So if we take the example of gasoline again, for an engine, a gasoline engine to run properly, the RVP of gasoline must be at a specific point. If the RVP is too high or too low, the engine does not run right. And then finally, there's a safety aspect to RVP. Storage containers, whether big or small, are designed to handle a specific RVP for products. So by monitoring the RVP, we can make sure that the storage container can handle the product that it will store. To my right is a 3D model of the P700. The P700 is composed of 3 enclosures. The bottom enclosure, at the bottom right, is a measurements enclosure where the measurement actually takes place. The top right enclosure is the electronics enclosure, where the signals are processed. And to the top left, we have a signal and power connection box. The P700 weighs about 500 pounds, including the stand. The total dimensions of the analyzer is about 3 feet wide by 6 feet tall. In the following animation, we will go over how does the analyzer actually make the RVP measurement. In this animation, you will see to the right a graph of the pressure gauge as the pressure changes inside the measuring cell. The first step of the measurement is to bring the measuring cell to 100 degrees Fahrenheit, at which it will be maintained throughout the entire process so that we can meet the 100 degrees Fahrenheit requirement for the RVP measurement. Once the cell has reached 100 degrees Fahrenheit, we will open the drain to remove any vapors left inside the measuring cell. We will then open the instrument air to purge any remaining liquid that might be left in the cell. Once the cell is purged, we will then remove 1/5 or 1 part of the volumes in order to prepare the cell for the upcoming 4:1 ratio needed to do the RVP measurement. The air removed is sent to the sample bypass and discarded. Then we make a first pull of the sample in order to wash the flow path and remove any potential contaminants that could alter the RVP measurement. During this time, we can see a negative pressure on the cell. Once the sample has been loaded in the microsyringe, it is then injected inside the measuring cell that has been maintained all this time at 100 degrees Fahrenheit. Once the sample is loaded, we start the agitation to release the vapors of the sample and reach the RVP. Once the RVP is reached, it is recorded by the pressure gauge and the electronics, and the cycle is finished. We purge the measurement cell and get ready for the following analysis. Now that you know how the P700 measures RVP, there are a few more features I want to point out. The first one is that this analyzer is manufactured at our Bartek Orb factory in Chicago in the US. The system is rated for NEC CEC Division 1 and ATEX IEC-EX Zone 1. To do so, we use an EXD protection method, flame-proof, also commonly called explosion-proof. The system is correlated to the ASTM D323 and D5191. We correlate to other methods, although more commonly D323 and D5191 are the ones requested. The system uses a microsyringe to do the measurement. The entire measurement range goes up to 35 psi, 2.4 bars, and has a repeatability of 0.05 psi or 2.4 millibars. Finally, the measurement cycle takes about 5 minutes in total to obtain the result. This includes heating and cooling that might be required. Now, why is this analyzer so great? Well, first of all, it has the smallest sample size on the market. For those of you using expensive validation sample, this will allow you to use as little validation sample as possible, thus saving money over time. It also has the fastest full measurement available on the market. Other systems might give a result in less than 5 minutes, but those results are predicted using mathematical models and not true measurement. The system also has a bidirectional temperature controller. This means that the sample can come hotter or cooler than the RVP, and the analyzer will take care of modifying the temperature in order to do the RVP measurement at 100 degrees Fahrenheit. The system also has the ability to do a dual measurement, RVP and TV over L, more specifically VL20, thus combining two analyzers in one. Finally, our Bartek Orb facility in Chicago is capable of fully integrating the analyzer into skids or provide auxiliary items to enable a easier and smoother measurement of the RVP. Now, some of the applications where the P700 is commonly found. The RVP of gasoline is one of those. There are two subsections. The first one is just regular blending of gasoline, as you would find, for example, at refineries. The other one is RVP of blended gasoline when ethanol or butane, for example, are injected into the gasoline. Another application would be in the LPG and LNG market, where we monitor the RVP of condensate coming from stabilizers or coolers before they are used, for example, in the blending of crude. With hundreds of RVP analyzers installed all around the globe and decades of experience with analyzer systems, you can trust Bartek to provide reliable and high-quality solutions optimized for your needs and designed for tomorrow's requirement. Reach out to us and you will see the difference that expertise and excellence can bring to your projects. We will be talking soon. Take care.